We have equations to describe the motion of an object under conditions of constant acceleration. Now let's look at the relationships between the position, velocity, and acceleration graphs if an object is undergoing constant acceleration. So we have a whole tree of possibilities to follow here, starting with the assumption that the acceleration is constant. There are two possibilities. Either the acceleration is zero is a constant, or the acceleration is not zero. We'll explore that possibility on the next page. So this whole tree starts from the assumption that the acceleration is zero. And since acceleration is the instantaneous rate of change of the velocity, if the acceleration is zero, that means our velocity is not changing. Velocity is constant. So our acceleration graph looks like this. And we have then two possibilities. Either the velocity is zero, because zero is a constant, or the velocity is not zero. If the velocity is zero, the graph looks like this. Because velocity is the instantaneous rate of change of the position, a zero velocity means that the position is not changing, or the position is constant. So your position graph could look like this. You're at the same position at every moment in time, position not changing. So this graph is linear, and a linear position graph tells us that the acceleration is zero. Moreover, this graph has zero slope. So a position graph with zero slope tells us that the velocity is zero because position is constant, not changing. Okay, let's come back up the tree to the case of zero acceleration but non-zero velocity. Then we can use this constant velocity equation, delta x, our displacement, equals v times delta t. This equation tells us that our position versus time graph is going to be linear, and the slope of that line is going to be the velocity v. There are two possibilities. Either that velocity is positive or it's negative. Positive constant velocity or a negative constant velocity. If the velocity is constant and positive, that gives us a position versus time graph that's linear with a positive slope. If the velocity is constant but negative, that gives us a position versus time graph that's also linear but with a negative slope. So if you see a position versus time graph like this, it tells you that because it's linear, the acceleration must be zero, and because the slope is positive, the velocity must be zero. Its position is getting more positive. It's moving in the positive x direction. Whereas this one, the position versus time graph is linear, which tells you that the acceleration is zero, and it has a negative slope, which tells you that the velocity is less than zero. It's moving in the negative x direction. All right, so those are all the possibilities for constant zero acceleration. Now let's look at the case of constant but non-zero acceleration. All right, so if our acceleration is constant but not zero, then we have these equations to work with. Our first two of the three constant acceleration kinematics equations. This one tells us that our velocity versus time graph will be linear, and the slope of it will be equal to the acceleration. This equation tells us that the position versus time graph is going to be quadratic, meaning it's going to be shaped like a parabola, and that parabola will be opening up if the acceleration is greater than zero. So if this coefficient here is positive, we get an up-opening parabola. Parabola will open down if the acceleration is negative. If this coefficient is negative, that parabola will open down. Okay, let's look at our possibilities here. So, acceleration is constant but not zero. That means it could either be a greater than zero constant, a positive constant, or it could be a negative constant. If the acceleration is positive, then our velocity versus time graph will look like this. It'll be linear with a positive slope. The slope here will be equal to the acceleration. If the acceleration is negative, velocity versus time will be linear, but with a negative slope. Slope here will be equal to the acceleration. The corresponding position graphs could look like this. Here, position versus time is an upward opening parabola because the acceleration is greater than zero. Over on this side, position versus time graph is opening down because the acceleration is less than zero. Remember that upward opening parabola Happy face because the acceleration is positive. Downward opening parabola, sad face, acceleration is negative. All right, let's look at that graph a little more, these two graphs a little more closely. At this special point right here, the bottom of this parabola, we could draw in our tangent line right there, and it would be horizontal, which tells us that right at that moment, the velocity, the instantaneous velocity, is equal to 0. We call that place where the velocity is 0, a turning point, because the particle is literally turning around right there. Here it's moving in the negative x direction, slows to a stop instantaneously, and then starts moving in the positive x direction. This is as far as it ever gets in the negative x direction, then it turns around and comes back. So our turning point is where the velocity is 0. And going back up to our velocity graph, we see that it corresponds to this moment right here. Where our velocity graph crosses 0, that's going to be our turning point right here. Prior to that moment, if I draw in my tangent line, I see that slope is negative, which tells me that the velocity is negative throughout this part of the graph, which we know because the object is moving in the negative direction. Over here, on this side, if I draw in my tangent line, that has a positive slope, which tells us that the velocity is positive over here. The object is moving in the positive x direction. And these 3 points correspond to this graph here. From here to here, the velocity is less than 0. The velocity is negative throughout here, meaning the velocity is negative along here. The object is moving in the negative direction. There, where it crosses 0, we have our turning point, and beyond that, the velocity is positive. It's in the positive territory up here. So our velocity is positive because now we are moving in the positive x direction. Similarly, over on this graph, we have a turning point right there where our tangent is horizontal, which tells us that right there, the velocity is 0. Corresponds to where this line crosses 0 on our velocity graph. Prior to that moment, our tangent line has a positive slope, the greater than 0, over here because the velocity is in positive territory up here. On this side, slope of the tangent line is negative because our velocities are negative over here. So this is a turning point once again. Turning point right there. And I should probably indicate that right there also is our turning point. Where our velocity graph crosses 0, it's going to correspond to a turning point. These points correspond to each other. Okay, now let's have some exercises for you to practice these relationships. I'll go through the first 3 with you, then the first 4. Then you can do the next 12. So I have here a set of 16 graphs. Some of them are position versus time. Some of them are velocity versus time. And on each one, what I want you to do is identify what can you tell about the acceleration of that object and what can you tell about the velocity of that object. First one, it's a velocity versus time graph. And we see that it has a positive slope. The velocity is getting more positive. It starts out very negative and approaches 0. The slope of it tells you the acceleration. It's a positive slope, so we can tell that the acceleration is greater than 0 for this object. Next one, this is position versus time graph. All right, we see that it's a curve, so we know that it's accelerating. We're going to assume constant acceleration, potentially, if we see a curve like this. So we know it's accelerating, and this is part of a downward opening parabola. It's not the entire parabola, but you can see that it's part of a downward opening parabola, which tells us right there that the acceleration is negative, part of a sad face, negative acceleration. The velocity, however, well, this object is moving in the positive x direction the whole time. If we draw in tangent lines anywhere, we see that they have positive slope. So that tells us that the velocity is positive from the tangent lines, and the shape of the curve tells us the acceleration is negative. Next one. Okay, position versus time, and we see that it's a curve, so it's accelerating, and it's part of an upward opening parabola. Happy face, that tells us that the acceleration is positive. What about the velocity? Well, it's moving in the negative x direction. Our tangent lines throughout this region have negative slope, so our velocity is less than 0 in this case. This graph over here, it's another velocity versus time, and it's a curve. But if velocity versus time is a curve, what does that mean? Well, the slope of the tangent line is the acceleration here. So the acceleration is positive there, and it's positive here, but it's changed. The acceleration has changed from here to here. If the velocity versus time graph is a curve, that tells us that the acceleration is not constant. The acceleration is changing. So in this case, the acceleration is not constant at all, and that's the only conclusion we can draw. Okay, I want you to pause the video and draw what conclusions you can about the remaining 12 graphs. All right, here we go. Let's look at these together. This graph, okay, upward opening, that's positive acceleration, moving in the negative direction, that's a negative velocity. This one is linear, so the acceleration is 0, and the velocity is positive because we have a positive slope here moving in the positive direction. Here again, position versus time is linear, which tells us acceleration is 0, and it's moving in the positive x direction. Velocity is positive. So note we have the same conclusions for these two graphs because the shape is the same. It doesn't matter that this position is down here and this position is up here. The shapes are both the same. So we draw the same conclusions. Here we have velocity versus time is a constant. So velocity is not changing. That tells us that the acceleration is 0. Down here, okay, velocity versus time, we have a negative slope here, which tells us that the acceleration is less than 0. Our velocity is getting more negative with time. Right there, we would have a turning point. On our position versus time graph, here we have part of a downward curve, so the acceleration is negative, but we're moving in the positive x direction the whole time, so our velocity is positive. Here we have velocity versus time. It is a curve once again. We cannot possibly have a curving velocity versus time graph with constant acceleration. That tells us that the acceleration is changing. We couldn't use our constant acceleration equations in this case. Position versus time, part of a downward curve, so that is a negative acceleration, and we're moving in the negative x direction. Negative slopes on our tangent lines, so the velocity there is negative. Are you getting all of these? Position versus time, upward curve, that's a positive acceleration, and we're moving in the positive direction. So that's a positive velocity. Here, position versus time is constant, which tells us that the acceleration is 0 and the velocity is 0. This object is not moving at all. Here we have, let's see, it's linear, position versus time, so acceleration is 0 because it's linear, and we're moving in the negative x direction. Negative slope, so the velocity is less than 0. And on this last one here, position versus time, we've got a curve that looks like this, as if at one moment in time we are at two different places at once, or maybe if we're moving in this direction, suddenly we turn around and or we're going backwards in time, or maybe we were going this way, then we turned around going backwards in time. This graph seems to show that an object is time traveling, which is not possible. So a graph like this is total nonsense. In this course, time travel will not be permitted. Sorry, Doc.